So considerations when you train in mixed precision, right? So the main questions are which operations to do in single precision, which operations to do in reduced precision. What to store in single precision, what to store in reduced precision. So it's instructive to walk through various neural network layer or operation types and consider them separately, which we can then sort of concatenate into one fairly simple recipe. So let's do that. So guideline number one is whenever you do weight updates or to any kind of training task, weight update is a fundamental operation, right? Because you move forward, backwards, and now you update your weights with the gradients. One thing to consider is that FP16, and especially Mantissa, is sufficient for some networks, but there are also networks that require weight update to be carried out in FP32. So there's slightly more detail on that here. So if we look at two, let's say we're just adding two values in FP16. Right? So FP16 format has 10-bit Mantissa, which implies that if you are adding two values and the ratio of their magnitudes is 2048 or greater, then the sum is really just a larger magnitude value. Right? And the idea there is that, well, you have 10-bit Mantissa. To do the addition, you have to align the binary points, which means you'll shift the smaller value to the right. And if you shift it by 11 positions, you really shift it completely out and it just becomes zeros. Right? This also happens in FP32, except that FP32 Mantissa is greater. And the reason this can come up when doing weight updates is we have situations where the weight that you're trying to update is substantially higher than the gradient value corresponding to that weight multiplied with the learning rate. And that's not that difficult to see because if we look at learning rates such as 0.01 or 0.001, if you just take a value multiplied by 0.01, that's corresponding to adding a ratio between them of about 2 to the 7th power. 0.001 leads to about 2 to the 10th ratio, right? So you are starting to run out of the Mantissa bits in those cases. So if your learning rates don't really drop that low, you're fine. So as I said, a number of networks are fine with FP16 weight updates, but especially some recurrent networks do require FP32 updates. Therefore, we have this conservative recommendation is that whenever you update weights, you really maintain a master copy of weights in single precision, and you update them in single precision. But then to speed up the forward and backward passes, you make an FP16 copy of those weights and use them for forward propagation and back propagation, but keep updating this master copy. And we'll have the full recipe in a few slides. Now, if FP32 storage is a burden when training, by all means, try FP16. You may have one of those networks where update is perfectly fine with FP16 math and storage. So any questions on weight update? All right, perfectly clear. OK, another guideline is pointwise operations, right? So weight update is really sort of the training procedure. Now, neural network will have a number of pointwise operations. So those will be your activations, or I should say nonlinearity, such as ReLU, tanh, sigmoid, and so forth. You also have, let's say, pointwise adds, scale, bias, and other operations. So the guidance is there is that FP16 storage is perfectly safe for the vast majority of these operations. Now, some of them would require to be, their output to be written out in FP32. And these are the operations where, if you think about the operation F, and we compare the input magnitude to the output magnitude. So for example, exponential, right? So if you can take an input, put it through a function, and its magnitude can increase dramatically, these functions are safest to leave in FP32. Just to avoid the possibility of overflow. So some layers to consider are exponentials, squares, logs. You know, if you take a log of a small fraction, you may get a large magnitude negative value. Cross entropy falls into that category because it does have log as a basic operation there. Another thing, so FP32 math in these situations, I should have said math instead of accumulation, really does not have impact on the speed of training because all of these layers are really limited by bandwidth, right? You are reading some number of bytes, you're carrying out one, maybe a couple of math operations, and you are writing those bytes out. Well, if you think about Volta GPU, in half precision or tensor core ops have well over 100 teraflops per second potential, whereas if you look at memory bandwidth, it's just under 1 terabyte per second. So you have this 2 orders of magnitude ratio of math throughput versus memory throughput. Therefore, for operations that do very little math, math is perfectly fine in FP32. It'll have no impact on the speed of training. So this sort of leads to conservative recommendation is, leave pointwise operations in FP32 if they're well known, or if they're new operations. And then for the ones that we know, it's safe to do them in single precision, or at least, in half precision to write them out, such as ReLU, sigmoid, that have sort of very narrow range of output. Convert those to FP16 and save bandwidth to improve performance. So any questions on pointwise operations? Yes?
If I keep the FP32 copy and FP16 copy, then I'm not really gaining on memory.
Correct. So the question was, if you keep both an FP32 and an FP16 copies, you're not really saving memory, you actually are spending more cost. So yeah, so unlike the weights for the update where you should keep an FP32 copy and an FP16 copy just to be conservative, for all of these operations, you don't have two copies. So if you decide, for example, to leave, let's say, cross-entropy layer in FP32, you would not have an FP16 copy of that. It effectively has no weights. So this really just talks about, when we talk about storage, we're talking about input and output tensors. So those you would cast into a particular type and leave it alone, and no other type would be stored.
Well, how much memory do I save?
If you go to FP16, you'd be saving half the memory. If you don't convert the inputs and outputs to FP16, then there are no savings for that particular operation. So up to 50% savings, I would say. Okay, other operations are reductions, right? So if you think about the categories of operations you encounter in a neural net. So reduction does come up in L1 norm, L2 norm, softmax. Effectively, whenever you have a sum of a large number of values, you're performing a reduction, right? From basically a vector down to a single scalar. We recommend FP32 math in these cases because, again, you're summing up a lot of values. They can be varying in their magnitudes. So just like for weight update, we had to consider different magnitudes and what kind of effect they may have on addition. Well, here you're doing a lot of additions and nothing else. So leave math in FP32. You'll avoid the possibility of an overflow in some cases. And again, you will not affect the speed because here, you are reading 2 or 4 bytes and doing one arithmetic operation per those 4 bytes read. So you're nowhere near close math-limited regime, so really just worry about saving bandwidth. Storage, when we think about it, so output should be FP32 because you've just accumulated a large number of values. Leave that in FP32 to be consumed by the following layer. Input can actually be left in FP16. So there are kernels, or you can write code that reads FP16 values, converts them to FP32 on the fly, and sums them up in FP32. And if you do that, then actually you do save some bandwidth, right? So in read, you're consuming half the bandwidth compared to single precision. The write from a reduction is negligible because you're writing out a single scalar. So the recommendation here is math in FP32, storage, input is FP16, output is FP32. And it really depends on the training framework that you use, whether it allows to use a different input and output tensor type per operation. So if they do allow that, we highly recommend that you go with FP16 inputs. If your framework does not allow different input and output types for an operation, then what you would end up doing is cast the inputs to FP32 and then do a reduction to ensure that the output is in single precision. Yep. Okay, so the question is, what is the cost of the conversion from FP16 to FP32? So on hardware itself, so NVIDIA GPUs for many generations now have had conversion instructions between FP16 and FP32 and FP64 and so forth. For these layers, they're basically zero cost. It's a single instruction that does the conversion. In a number of cases, they even do it in a vectorized fashion. Now, the cost in the framework can depend on how the framework interprets it. So if the framework does have the ability to read, let's say, half precision into a function, and inside that function convert to a different type, then cost is zero. However, if the framework doesn't have that functionality and you have to put in an explicit cast, then you're basically putting in a memory copy. So you'll read FP16, and the cast operation will have a kernel that will convert on the GPU to FP32 and write out FP32. So a cast operation basically gives you a round trip to memory, which, depending on your network, may add significant overhead or may not. It really depends on the network structure. Okay, so one quick note on the normalization and loss layers, right? So they obviously exist in every single network. And they really are a combination of other operations when you think about them, right? So batch normalization has reductions implied in there, some scaling, squares, square roots, and so forth. So usually, as I mentioned, they're constructed out of reductions, which we just saw, as well as operations like squares and exponentials, which can have magnitude changes from input to output. So because of these reasons, it's safest to leave these layers in FP32. So storage, input, and normalized output at the end, those can be in FP16. Right? Because what you have is you have data that's coming in as FP16. And after all the normalization operations, they'll still be kind of centered in the FP16 representable range. And that has been confirmed with many networks. However, in between, you may have many intermediate operations. And that really depends on how you are coding up these normalizations or loss functions in your network. If you're using standard things like softmax, cross-entropy, many frameworks will have actually a dedicated function to do all of those operations. If you are designing something exotic yourself, you will likely start by combining addition layers, reduction layers to compute the value by which to normalize. So all of those intermediate values that you sort of stitch together different other operations, between them it's safest to leave the storage in FP32, right? Because if you, let's say, compute the L2 norm of all the values in your activations, that's largely a large value, leave that in FP32. Now, ideally, whatever loss function or whatever normalization function gets designed, at some point, all of those individual ops would be fused into a single, let's say, function call that executes on GPU. So that's purely for speed or performance optimization, because what that would do, it would avoid all the round trips to memory. If you think about, let's say, computing L2 norm. In the primitive scenario, you would first compute the square of each value in the activations. Then you run a reduction kernel. Then you read a scalar and put it through a square root function. So that's 3 functions that you go, all of them that you use in sequence. All of them are memory limited, because you read values, do very little math, write them out. So by fusing them into a single operation, you avoid all those round trips, which means you'll run faster. You also avoid the need for any intermediate storage. Right? So actually you save space, and you don't have to worry about what to leave in FP32 or FP16. So if you do end up writing your own layers, strongly consider fusing any sort of exotic losses or normalizations. Okay, so I already sort of combined losses and probabilities together. So softmax, cross-entropy, some attentional modules, what they really do, they don't really normalize, but they might produce a set of probabilities. Right? So probabilities, by definition, would be in the 0 to 1 range. But they are an interesting case. And here, as you see, we recommend FP32 math and FP32 output for probabilities. Because especially as you have a large, let's say, vector of probabilities that all add up to 1, you are bound to have a number of very small probability values, especially as your network trains and learns and predicts better. Now, what we find is that even the very small probabilities, you'd like to retain them as values, not flush them to 0 for training purposes, because they still contribute some loss to be backpropagated to the network. So they do help to squeeze out the last percentage point or so in accuracy. So whenever you generate probabilities, leave them in FP32, because then they still contribute to the backpropagation and to weight updates. So questions about losses or normalizations? Nope. Great. Okay, so now sort of the best operations for tensor cores are convolutions and matrix multiplies. Right? And really, we've just gone through all the basic operations in a neural network when you think about it. Pointwise, reductions, convolutions, and matrix multiplies. Deep down underneath, they do end up being dot products. And as we've seen, Volta tensor cores really are set up to do a lot of dot products in parallel and very efficiently. So that's the perfect scenario to use tensor cores. They are incorporated into pretty much all the major frameworks nowadays. And by sort of looking at this link, you can see directions how to get a Docker container or instructions how to use tensor cores or enable them in various frameworks for training. Now, for training, as I mentioned earlier, whenever you use tensor cores, you want to use FP32 accumulation mode. So they will read FP16 inputs. They'll do all that product computation. They'll accumulate that product into FP32. And right before writing out the output to memory, they'll convert to FP16. So in our pretty extensive tests, we have seen that for all the convolution and matrix multiply or fully connected layers that we have looked at, FP16 input and FP16 output are perfectly fine. So recommendations here are really pretty simple. Storage is always going to be FP16, input and output tensors for these ops. And then for the ops, really the framework takes care of the details for you. It'll invoke tensor ops and do FP32 accumulation. So really this is sort of your biggest speed up opportunity. And we will look at performance a little bit later in the presentation. So questions on convolutions? Nope. Okay, let's see how we're doing on time. I should probably speed up. Okay, so summary so far. We've seen that, conservatively, keep FP32 master copy of weights and update weights in FP32. For math, either just do it in single precision, because for a lot of operations, memory is the limiter, so math doesn't matter, so just stay safe with FP32. Or use tensor cores, which do take FP16 inputs, but still sort of mix FP16 and FP32 math, using FP32 where it really matters, is in the accumulation. For storage, most layers can be left in FP16, or most tensors can be left in FP16, and then use FP32 for layers that output either probabilities, or can accumulate a large number of values into a sum, or can change the magnitude between input and the output. And again, for all of these cases, fusing can really solve a lot of performance problems, as well as eliminate the need for decisions whether to use FP32 or FP16. So I think it's interesting to look at sort of the breakdown of time on Volta GPUs by layer type, right? Since we said, okay, some layers should be left in FP32, some can use tensor cores. So if we look at ResNet 50, and that's on Volta, and that's purely single precision training, 73% of time is spent in convolutions, when the remaining 27 are batch norms, ReLUs, adds, and so forth, right? So this time can be sped up quite a bit by tensor cores. And the remaining layers can be sped up by maybe 2x, because you are saving memory bandwidth. Deep Speech 2, or one of the variants of Deep Speech 2, spends about 90% of time in convolutions and matrix multiplies. It has some convolutional layers, it has some fully connected layers, or as part of LSTM cells. And then 10% are dedicated to other. So that sort of gives you a picture that there are ample opportunities for speedups whenever using mixed precision training.